Welcome to Brain Vision.
The problem we have here is going to require just a tiny little bit of calculus and doing a derivative, but it's not bad at all. The problem is related a little bit to a previous one, but primarily it wants us to derive the expression for the bulk modulus given a certain pressure at absolute zero. So we're to take the derivative of that pressure and multiply by the negative volume. So if we get going here, we get the derivative of all that, which I'm going to reduce down all the constants here. This is a nice little trick for you, to some general constant called a, and then leave only the variable that changes as something left alone. This will keep things a lot cleaner. And another thing that I'm going to do is take the inverse of this, or sorry, just write it as v to the minus 5/3 because it's equivalent, but it just saves a little bit of writing and arithmetic to do it this way. So we get the derivative with respect to our new and improved p, which is just some constant a multiplied by v to the minus 5/3. And then this is really easy to take the derivative of. You just get minus v times a times minus 5/3 from this exponent here. And then you get v minus 5/3 minus 1, which is just minus 8/3, but it doesn't matter because this v multiplied by this v adds 1 to it. So if we write that out, then we get minus a times minus 5/3 times v to the minus 5/3. Well, here, I'll just write the whole thing. Minus 1 plus 1. But these, of course, cancel. And that leaves us with the bulk modulus is 5/3 times a times v to the minus 5/3. Except that's just what we started with an extra 5/3 in front of it. So we write it as 5/3 times p. And if you look, that is exactly what the problem says we should expect, which is a good thing that we are getting what we expect. And you see that my method of condensing down all of the constants is going to pretty much always save you a little bit of writing. So I highly recommend you go that route. But we do have a part B. So if this is part A, part B wants us to evaluate this bulk modulus for electrons in copper, which has a free electron concentration. So concentration is just N per V of 8.45 times 10 to the 28 meters per meters cubed. This you're just going to plug in for this, and everything else is a constant. So I'll just write it out here. You get a bulk modulus of 6.33 times 10 to the 10 pascals whenever you consider this particular concentration. And then finally, part C wants us to look at the real bulk modulus. So I will say this one is our we'll say this one's our real one, so we'll put an R. And the value for that is 1.4 times 10 to the 11 pascals. And based on our result in part B, what fraction of this is due to the free electrons? So we should simply divide our B by B real, and we get something like 0.45. So about 45% of the bulk modulus of copper is solely due to the free electrons in that copper. So, as the question says, that shows that free electrons do play a major role in making the metal resistant to compression. However, it also asks, what do we think is responsible for the remaining fraction of the bulk modulus? So, that remaining 55%. And the only thing that's left besides electrons are going to be the cations in the ions. So the actual atomic nuclei themselves are actually providing the rest of the pressure for metallic copper.